I'm Rick Douglas. I direct the Machine Learning for Social Science Lab. This is what the Machine Learning for Social Science Lab is and does. We're a division of the Center for Peace and Security Studies. Institutionally, we're a permanent fixture now on campus. We're dedicated to the intersection of a couple of different fields, political science, but also computer science, information science, and other parts of social science. We do a lot of work on things that be related to demography or sociology. Political science is our main substantive question, but we deal with a bunch of data and methods that are developed in other areas, including like economics. This intersection doesn't have a good name for it. It's sometimes called computational social science, data science, whatever the popular buzz term is for right now. What that means in practice is we focus on technical capabilities. We focus on technical capabilities that are needed to handle increasingly massive and complex data sets. We focus on technical capabilities that are increasingly developed and used outside of the social science and the machine learning community, everything coming out of Google, Facebook, these big tech companies. And we focus on technological capabilities that you're not going to get training in a typical social science graduate program. This is changing, but very slowly. And so a lot of the recent hires have been recent graduate students with these capabilities. So a lot of programs will have one or two people that specialize in something, but these capabilities are really the cutting edge. You're not going to find many people dedicated to working on this. We have a large and growing group of people working with us. For the leadership, you've already met Tom Scher, who's our recent deputy director hire. We have a number of graduate students that work with MSSL and are directly attached. We also have a large number of undergraduates. So given that data science is a buzzword, what is it? It is a lot of different things. It's everything from different kinds of data that are difficult to work with traditionally because it's long, it has millions of rows or billions of rows. Because it's wide, it has hundreds to millions of columns. Because of it's unstructured, like text or images. Videos even. Maybe it's a complicated structure like networks or geospatial information. And each of these areas have entire developed sections of computer science and information sciences dedicated to them. People who just get tenure on natural language processing, just a new algorithm they develop. And you're expected as a graduate student just to know how to do all of this immediately. This is year 3 or 4. Your dissertation, you require, all of a sudden you realize you need to understand Twitter data, and you're expected to understand whole branches of mathematics and computer science that have never been introduced to you. So one of the things that MSSL does is it tries to have a standing technological expertise that's on campus for you. We're doing this all the time, and if you have projects that you bring to us, we can give you advising and assistance and have some algorithms and computational capabilities ready to go. It's almost impossible to get good at all of these things. It's definitely impossible to get good at all of them during a typical graduate program. And so it's very important to have these institutional resources waiting for you when you realize you need that capability. Something about the lab that I'm very proud of, and this comes from a little bit of my time as postdocing in the math department for 3 years, is we run this like a natural science lab. It's an incredibly collaborative environment. It's organized around reusable code and software packages that are supposed to be lasting, standing things that are constantly used from here on out. It's not a bunch of one-off projects. It's not a bunch of one-off data sets. And also we're instilling the best practices in reproducible research. All of our code is online. All of our code is up on GitHub. We're all collaborating and directly working on everything together. And also we're sharing credit, something that you won't always see in a lot of different labs or a lot of different projects, is you always have the PI first author and then like 1 or 2 people thanked in the acknowledgement section. We run it like a natural science lab. Everyone who works on something gets their name on the paper. We have more data sets and more projects to work on than we have people. Sharing credit is not the constraint we have. It's human capital. We desperately need more people to come work with us and grind out just all of the data sets and all of the projects we have already on deck, much less in the coming years. So why do all this hard work? It looks like a pain in the ass. Why put all the effort into it? And I'll make a case for a couple of different reasons you'd want to do this. One is you want to measure more completely. You want to measure things that are hard to measure. You want to turn unstructured information into structured data. You want to understand the sequencing of events. You want to avoid mistakes with existing data or approaches, and you want to build resources, standing resources, before you know that you need them. And I'll step through some examples on all of these. This is kind of our flagship project that's going to be out the soonest. This is called the Named Entities for Social Science Project. That's the Loch Ness Monster. That's our mascot in the top right, Nessie. That's right. This is a universal list of persons, places, and things relevant to social science. Every large tech company has a team that's dedicated to this. Facebook calls it the persons, places, and things team. Social science doesn't have an equivalent of this. We're starting with the 5.4 million entities that are available on Wikipedia. And we're standardizing, just as our first product, a list of all of the states that have ever existed and the subset of those that have been sovereign states. And there are some common international relations data sets you probably know about, like the Correlates of War state list. PRIO has a state list. We are developing an ontology of states and all the different properties that they can have. Everything from being a colony to a protectorate to being a colonizer to being militarily occupied, all of the different relations that the states can have with one another. We're tracking their growth and change over time, and we're finding hundreds of entities that aren't talked about in existing data sets. This is problematic because they're leaving out a lot of countries and polities that just aren't in Europe. The existing data sets are incredibly specific to things that were easy to study in English by European descended scholars. And we're finding lots and lots of different polities, lots of different kinds of polities that have been traditionally ignored by social science. And that has all sorts of implications for how you study conflict, political development, lots of different things. We're modeling how those entities have changed over time, including their borders and their geographies. So we're tracking the political boundaries of polities all the way back to 1800. The current existing data sets only go to 45. In the top left is a view of the world in 1800, and it's a little hard to see, but these white areas are unincorporated and the gray areas are incorporated. So about half the planet, or a third of the planet, is just completely unincorporated in 1800. And fast forward to today, every single square inch is owned by somebody and being taxed by somebody. And we think that's important. We think those are dramatically different political environments, especially when you think about something like conflict. Your odds of going to international war might be lower if there's just empty space or unincorporated space with indigenous people on it that you can expand into, versus today where if you want to grab an extra square mile of territory, you have to take it from someone with force. These are the kinds of covariates that we're tracking for these entities that we're developing. We're also tracking the genealogies of political entities. So this is a network graph. If you start in the top left, you can see Oahu, which joined the Kingdom of Hawaii, joined with some other islands to form the Kingdom of Hawaii, which then became the Provisional Government of Hawaii, the Republic of Hawaii, the Territory of Hawaii, and finally was incorporated as a state in the United States. So for every single polity and every single political entity we're tracking, we know their full history, how they joined, how they split apart, all of these details that currently we're not tracking at all. We just have state lists and occasionally when they go to war with one another. We're doing the same thing for international conflict. This is a comparison of a large number of existing conflict data sets. They vary dramatically in the time periods that they cover. We also found they vary dramatically in the events that they cover. So basically every conflict data set disagrees with every other one about what wars have happened and what battles have happened, which is not good. It's not a good thing. So similarly with polities, we have an ontology of different kinds of conflicts. We're in the process of unifying all of the different conflict data sets into one large master one with the hopes of having the most comprehensive list of international violence that has taken place going back thousands of years. Another goal for data science is to measure things that are hard to measure. Here's an example from my time in the math department where we developed a real-time population census measured down to very small 55 by 55 kilometer grid squares. And the way we did that was using cell phone calls. We were able to correlate cell phone patterns at this very small geographic level with the last known census. We were fortunate. This is some data from Milan, Italy. The census happened relatively soon to the cell phone data we had access to. So we combined satellite imagery which we turned into land cover mapping, with the cell phone call patterns of individuals, and developed a model that actually could predict how many people lived in that 55 kilometer square area with fairly high accuracy. With the goals, using a system like this, you can measure population changes between censuses, which are kind of far apart, and also measure population that's underreported by the census, because a lot of people don't answer that door for all sorts of political reasons. And so we were able to identify refugee communities, immigrant communities that were missed by the institutional census process, but we were able to capture through this other mechanism. Global land logistics. Terrain and logistics traveling between different points is a major constraint in trade. It's a major constraint in international conflict. It's hard to define, though. How hard is it to go across a certain amount of territory, especially if you have engineering battalions that can cross swamps and build bridges? What does it mean to be difficult? We used kind of a clever trick. We looked at historical road patterns. Specifically Roman roads that were built between 1300 and 1600. The Romans were very good at building roads, and they were also incredibly interested in getting straight roads. The straighter the road, the faster your military could travel on it, and the more money you can make on a trade route because you had less things to go around. So what we did was we first got data on the historical road map, and then we got data on historical cities and towns on that network, and we drew counterfactual shortest distances that you could have crossed. If there was no mountain in the way, you would have just taken a straight line between these 2 points. But instead, we saw the Roman engineers went all the way around the mountain to build the road because they had to. And using that information, we were able to compare every single point on the planet to every counterfactual point of how you would have gone if you were able to. And using that, we were able to back out how hard it was to cross terrain globally. This is a gigapixel terrain map for the entire planet, with blue being the hardest to cross and red being the easiest to cross, which, just as a gut check, anyone who knows kind of World War II military history, Rommel was able to cross hundreds of kilometers a day back and forth. This terrain is incredibly easy to cross, whereas the campaigns in Italy, you can see all these mountainous areas that are just a complete pain. Those terrain effects have real consequences for military fighting and defensiveness and things like that. We're doing the same thing for global naval logistics. We think naval travel are really important for trade and military conflict, but it's hard to understand how these sea lanes, these ports matter over time. So what we did was we found a data set actually collected for global warming studies. They've got the log books of sailing ships going back to the 1600s. Sailors wrote down latitude, longitude, or whatever the equivalent was in that historical period, the types of weather, the time of day, etc. For navigation purposes and also military recording. Those records have been digitized for global warming studies, because now we have a historical record of temperature going back hundreds of years by human recorded temperature. We've collected those records, and we've started producing sailing patterns going back hundreds of years between every ship that sailed from one port to another port. So we know what route they took, we know how long it took them to go that route, and we also know the historical wind patterns, because these are relatively consistent over time. So we're able to say how fast a certain kind of ship in a certain century could have gone on a certain route based on the technology of the day and the weather of the day. And so with this, we're able to back out how hard it is in what season to go between any 2 points on any 2 coasts in the world, all going back hundreds of years. If you're interested in military technology, this is a project that Andres has spearheaded. This is a survey for 50 countries on 150 different military technologies. And it scores each country on 0 to 5 on how capable they are on things like certain kinds of artillery, certain kinds of nuclear weapons, certain kinds of production capabilities. And we've used some neural networks and latent variable models to reduce those 150 technologies into a smaller set of latent measures of how capable you are. So we're able to score every country on how militarily advanced they are, from most advanced to least advanced. And we're also able to score specific technologies on how hard they are to develop. So just one thing I learned is that chemical and biological weapons are super easy to make. If you just have a chem department at a university, you're pretty much good to go. That was scary to find out. But things like directed energy weapons and electronics were still relatively rare when the survey was taken. Another opportunity from this kind of process is turning unstructured data into structured data. So in the very top right, I have just a sentence or two from the Cuban Missile Crisis. Most of our data in the social sciences, or in conflict studies at least, are stuck in this format, in narrative format. Historical accounts of either primary or secondary, people recounting stories, recounting the series of events that took place, but you can't put this into a regression. And you can't standardize it across different narratives, across different storytellers over different periods of time. What we did was we developed a graphical user interface that showed to a coder sentence by sentence this narrative, and then gave them options to put all the details, all the facts in this paragraph or in these sentences into a structured format that's comparable across every single sentence, across every single narrative that we have access to. And what we were able to do is we now have 470 crises coded sentence by sentence. It's over 10,000 specific events of every single play-by-play that happened during these international crises, like the Cuban Missile Crisis. This is what it looks like when you have multiple sentences, and so you can start to see first state A did this, then B did this, then A reacted. You can start to understand how cause and effect in international relations works. And this is also towards a general theory of diplomacy. I don't know if you're very familiar with this yet, but one thing you'll notice about international relations is that most of it's about billiard balls and how states just kind of theoretically should bounce into one another, but all of the little nitty-gritty of how they actually talk to each other and make threats and those little play-by-plays, international relations doesn't care that much about it, or at least as much as it should. Diplomatic historians are the ones who traditionally work on that. Part of the reason for that is because it's really hard to do. It's really hard to systematize. We are working to doing that at a large scale, hopefully bringing diplomatic history into the quantitative realm. Another thing that is a really big issue for me that I care a lot about is discovering problems or avoiding mistakes in using data inappropriately, or finding ways that other people have used data inappropriately. Here is just a cautionary tale about a very common political science data set, the MIDS data set, the Militarized Interstate Dispute data set, which in theory tracks conflict for over 200 years. But there are lots of different kinds of events in this data, and you might think that the reporting over 2 centuries varies a little bit when CNN comes on, where that didn't exist in earlier periods. And so if you took the data literally, it would look like conflict's getting more and more common for some reason. There's just a lot more territorial disputes than there used to be. So what we did is we did a little bit of machine learning work where we clustered data into different types that had similar properties. And we found about 7 different types of events. And for some of them, like the big ones, the war-related ones, we found a consistent pattern over time. The number of events looked pretty regular. There's no dramatic increase over time or decrease. It looks like the war events are spiking around World War I, World War II, known conflicts in international relations. For land battles, non-fatal land battles, seizures and territorial revisions, we see this huge temporal trend over time on both of these. And what we think is happening is that it's not that these events are actually becoming more common, it's that it's becoming more commonly reported and easier for undergrads to find and report. And so now we've shown that at a minimum you should be disaggregating your conflict data into a couple of different types. Some you're going to be able to trust the temporal trend, and other times you're going to have to compensate for it and not take it on face value. This is some work based on my dissertation about an existing data set from the Vietnam War. If you're interested in civil war or rebellions or things like terrorism or selective targeting in a conflict, the Vietnam War has as good, if not better, data than that came out of Iraq and Afghanistan, the SIGAX type data that have been released recently. But unfortunately, the formats and the history of that data is very complicated, and it's been kind of used in inappropriate ways in the past. This particular data set was on selective targetings. These are civilians in South Vietnam that the US military, along with South Vietnam, targeted for arrest or assassination. Had a huge record of over 70,000 people in this data set. An existing project by Kalivas and Coker in 2007 did some quick analysis with it based on the codebook they had access to, and they came to this really surprising conclusion that important suspects were actually more likely to get away. The ones the government knew the most about had the big, thickest file on. For some reason, they never caught those guys. It's always the farmer that they caught. It's always the logistics person in the back that they were getting their hands on and actually killing or capturing. And they wrote it up, and they had this really interesting finding. I did a little bit of machine learning work on this. This is what that data set looks like. There's an algorithm called co-clustering where you can shuffle the rows and the columns based on missingness. And one of the things I discovered is that the reason they have this finding is because there are two different records in the data set. There are people they haven't caught yet, the really important ones with the thick files, and there are all the people that they caught. And because these two data sets are mutually exclusive, they were basically saying every person that we haven't caught yet will just keep their file open, and every time we just come across somebody, we'll write it down here. It's not that these people are harder to catch, it's just that's the pile that got stuck on top and put into the data set. It's not this systematic difference, it's exactly about how it's recorded. It turns out this is a really tricky mistake to find because the code book is wrong, and the data sets went from punch cards on an IBM 360 mainframe that was the size of a small house to magnetic recording tape. And so one of these values should have been listed as just missing, but it was imputed as a 0, and that doesn't show up in any code book anywhere. So if you take even the documentation of data literally, you're going to make unfindable mistakes. And machine learning is a way for us to kind of back out that institutional data generating process and avoid those mistakes. One last one on this is that georeferencing is a common task where you have a terrorist event or a bombing of a village or some kind of event, and you try to take the text that describes where it happened and find an exact latitude and longitude. This is the place it happened. That's the common task of georeferencing. People do this step without explaining why they made the choices they did or how they did it. And it turns out there's lots and lots of different ways to make this coding step. We looked at 13 different ways and found which one you pick will give you completely different answers when you do your statistical analysis. And not like small mistakes. We showed that your statistical significance will flip, your sign will flip, you'll get the opposite answer if you make this arbitrary decision wrong. And no one reports why they decide the way they do. It's usually in the appendix somewhere, and it's usually like undergrads did it this way. And we found that it's actually really important to pay attention to that step. And I'll finish on this. We're a big fan of building resources before you need them. And so while we have all these projects ongoing, we're compiling a very large corpus of text. Everything from the Common Crawl web scrape, which is over, I think it's 80 terabytes of text. Everything from Wikidata and Wikipedia. We're compiling all of the international news. We're soon going to be able to cover almost the whole period from about 1850 to today in international news. So if you're interested in anything that was written about in those 2 centuries, we'll have data for you on it. And also political texts like congressional record or parliamentary debates. So if you're interested in domestic politics or the intersection between domestic politics and international relations, we'll have you covered there. And we're also slowly but surely building a standing army of hand coders. So this is having undergraduates in place with GUIs and computers set up for them to work on, and the standard operating procedures so that every time you have a new coding task, there's already people waiting to do it. And if we can't do it locally, we know how to use mechanical Turkers and outsource to commercial companies. So when you get a good idea, we can act on it very quickly.